Hi, I'm Evan Lewis from the Evan eCent channel again, and this time we're going to be talking about gear train issues in converting a imperial lathe to cut metric threads or to convert a metric lathe to cut imperial threads. It's a very common question, and often people are faced with wanting to buy a special set of transposing gears to do this, but they are rather expensive. And one alternative is to use my computer program, Ride the Gear Train, to find out whether the gears you already have can be used to cut the particular metric thread you want on an imperial lathe, or vice versa. I'm going to show you an equation that I developed for working out how to design these transposing gears, and they don't always have to be at 127, 100 transposing gears. There are dozens of alternatives that are approximations to it. They're not 100% perfect. It had puzzled me for some time. How do you work out what pairs of gears might work for doing a complete conversion? You see, if you use Ride the Gear Train, you can find out a solution for a particular thread, but it doesn't give you a general solution for all metric threads. And this method that I've derived is for all metric threads, so it really is an equivalent to the 127/100 compound gear combination. This is a standard compound gear used for converting an imperial lathe to cut metric threads. Right now we want to focus on the compound gear, which is a 127 tooth gear connected to a 100 tooth gear. The other gears, the stud and lead screw gears, can be altered later to make different pitches, but the transposing gears or compound gear, especially the 127 tooth gear, is instrumental in changing it from imperial to metric. Now the first thing we have to do is decide which gears are drivers and which are driven. So the stud gear here is a driver gear, and the 127 tooth gear is driven, and the next compound gear is a driver again. So when we come to calculate the gear ratio introduced by this compound gear, it's actually compound 2 over compound 1. That might seem counterintuitive, but if you look back at the driver-driven series, you'll see why that is. So we calculate the gear ratio as compound 2 over compound 1, which is 127 over 100, giving a ratio of 1.27. So what's so magical about 1.27? Well, we can multiply it by almost any number by using other gears in the gear train, so let's try multiplying it by 2. Now you'll probably recognize that as being a very special number. It's the number of centimeters in 1 inch. So if we have inches and want to convert them to centimeters, we would multiply by 2.54. But conversely, if you wanted to convert centimeters to inches, we'd divide by 2.54. And to do that, all we have to do is take this pair of compound gears and flip them over, and we get the inverse ratio. So it can be used for either converting metric to imperial or imperial to metric. But the 100 tooth gear can be replaced by other gears if the change can be compensated by other gears in the gear train. For example, the metric Boxford lathe uses a 135 gear connected to a 127 tooth gear, and you might notice that 135 divided by 45 is 3, and they do combine that with the 45 tooth gear as a stud gear. Another common variant is 127 over 100, so the 100 tooth gear is replaced by a 120 tooth gear, and one of the reasons for doing this is that using two tooth counts that are very, very close means that it's much easier to mesh small gears into the gap between the two sizes. So it helps to make these two sizes as close together as possible, and then use other gears in the gear train to compensate. Let's look at our metric lathes with a 3mm pitch lead screw using a 127/135 compound gear, and this is combined with a stud gear of 45 and a lead screw gear of 40, giving the following equation: 3mm pitch multiplied by 127 over 135 and multiplied by 45 over 40 gives 3.175 millimeters, which happens to be exactly 1/8 of an inch, or 8 threads per inch. Although the 127 tooth gear gives perfect conversion, other combinations can be used if a small error is acceptable. The most common of these is a compound gear pair consisting of an 80 tooth gear connected to a 63 tooth gear. And this ratio is 1.2698, which of course is very close to 1.27 and only introduces a tiny error of 0.0125%. If we multiply 63 by 2, we get 126, and you immediately see why it is so close to 127. But we can also divide 63 by 3 and get another integer, 21. And some lathes have a 21 compound gear combined with 20 built into the gearbox because it's so small and convenient to install. And you could also multiply that by 2 and use a 42-tooth gear. So all of those gears, 127, 63, 21, 42, can all be used for metric-imperial conversion. Let's go back to the 127-tooth gear and see how it's applied to the imperial lathe with an 8 thread per inch lead screw. That has an 1/8 of an inch pitch. 1/8 of an inch times 25.4 gives 3.175 millimeters pitch. So that's just the standard 1/8 of an inch converted into metric. 3.175 times the ratio we get with our conversion gears, 100/127, gives 2.5 millimeters pitch. This makes an 8 thread per inch lead screw behave like a 2.5 millimeter pitch lead screw. So that's another way of looking at this conversion and leads to the next step. In a minute I'll show you an equation that I derived for calculating more general conversions like this. This resulted in this table. In the columns you can see labeled 4 threads per inch, 6, 8, 12, 16. And under each of those you see rows which are labeled number of millimeters pitch. So if you have a lathe with a 4 thread per inch lead screw and you decide you wanted to make it behave like a lathe with a 3 millimeter pitch, you look down that column to the 3 millimeter line and you'll see a number, 2.11667. That's the conversion ratio you need to make this happen. Now we can ride the gear train to find out all the different pairs of gears which will give this ratio. Another example which we've just looked at is taking an imperial lathe with 8 threads per inch and we want to make it look like it has 2.5 millimeters pitch. So we go down to that row and we see a ratio 1.27, and that's the ratio we've recently been dealing with, which can be achieved with a 127-tooth gear and a 100-tooth gear to give 1.27. So this is a generalized method of making all of these different kinds of conversions, not just the standard 1.27, but various other ratios you see here. This table can also be used the other way around, that is to make a metric lathe appear like an imperial lathe. So if we have a metric lathe with a 2 millimeter pitch lead screw and we wanted to make it look as though it was 16 threads per inch, we would use a ratio of 0.79375. This is the equation that I derived to generate this table. It gives the ratio as 25.4 divided by Li times Lm, where Lm is the pitch of the desired lead screw and Li is the threads per inch of the imperial lead screw. Lm for metric and Li for imperial. Now I haven't actually checked this out to see how this one works, but this is an example I've pulled up. We were wanting to make an 8 thread per inch imperial lathe behave like a 3 millimeter metric lathe, and the ratio is 1.05833. Okay, so let's ride the gear train. So here's Ride the Gear Train, introductory page, and below that we have the quick start guide, which tells you the steps you go through for standard thread problems. And we have the main menu, and steps 1 to 5 for the thread calculations, so normal gear train calculations, and you press 6 to run. But let's scroll on further down into the other engineering applications, and we find one here that's marked metric to imperial conversion gears. Click that and we come up with this page, which comes up with some instructions, and this shows the equation we've just been talking about and the table we just showed. So right at the very bottom, we scroll right down, we can put in a ratio here and it'll tell us what gears to use. We don't actually have a gear combination to enter here. The gear ratio number, which was 1.05833, actually a lot of threes, and return. And here's a list of all the pairs of gears that could possibly be used to make this gear ratio, and this shows the relative error that you would have if you chose these. And of course this error comes about because we have to use integer numbers for the number of teeth on the gears. You can't have 1.5 teeth on a gear, or 10.5. So we look down this list and see if we can find ones that have very low error. Here's one here, 18 and 17. They're marked in red because they're the important ones. Same ratio, 36/34. And actually I've seen that one being used. Or 54/51. Or 55/52. 72/68. 73/69. 90/85, 91/86, 92/87, and that's quite enough to go through, but there are a few more too. So you can see there are lots of different solutions that are quite adequate for doing this conversion without necessarily having to use the 127 setup. And this makes it behave as though there are 3mm pitch in the lead screw. So if we want to take this a step further, we could choose one of these, say a nice middle one, 36/34. When we're finished with this list, we go to the bottom and return to the main menu. Let's choose an imperial lathe with no gearbox to keep it a bit simpler, and we'll design our gear train. We want a lead screw with 8 threads per inch. That's been entered for us. And we want one compound gear, and this is the illustration of one compound gear. You've got a stud gear, your double compound gear, and then the lead screw gear. So that's the design we want. And it so happens in this case it's most convenient to use not automatic, because I want to be able to enter my own compound gear to do this. Go back to the menu, scroll down, enter our own gears as the next question, 2B, or not to be, as the case may be. And we'll keep this previous list of change gears, just a rather random list. Actually, it's a list of gears that often comes with a box-fed lathe. And now, instead of using the 127/100 compound gear, actually the gears that we want are 36 and 34. And now we'll see if this allows us to cut an imperial thread. So the third question is what type of thread we want to cut, and we can choose an imperial thread, or we can do feed rates. We can scroll down to the metric section, and yes, we want a metric thread and enter millimeters pitch. So it's already set. Return. Back to the menu again. Acceptable error is set at 1%. It's probably good enough. And let's decide what kind of pitch we want. So this allows us to enter a single pitch set on 6mm, which is a bit unusual for a metric thread. Let's try 1.5mm pitch. Return to menu. And at this stage we've entered all the data we want to. We don't need to use a range or reference tables. We're just going to use 5A, which is a simple one to enter a single thread. Now we're ready to run it. See what happens. Only got one result. It only has 0.3937% error, and we use a 16 tooth stud gear. The compound pair with 34 on compound 1 and 36 on compound 2, and the lead screw gear of 36, and that gives us a pitch of 1.4941 with that 0.39% error, which is probably fairly satisfactory. Draw, and we see what the gear train looks like. We've got 16 tooth stud gear, 34 tooth compound gear in the middle, 36 tooth compound gear attached in the background, and a 36 tooth gear on the stud gear. And it looks quite clear that these will fit together without any problem at all. Notice that there's a very little difference in size between the 34 and 36, so there's really no difficulty at all in making these gears mesh into that little gap. The fit test says there's no obvious problems with the fit, and these are the equations that can be used to calculate the gear train ratio, which is 0.47. So there you have it. We have a pair of compound gears that could be used to make it behave like a 3mm pitch, and it gave us a useful thread. Now, before I leave ride the gear train, I really should show you something that I think is quite important, and that is to ride the gear train with the gears you already have before you even consider going out and buying more gears or getting special transposing gears. So this is basically the similar process that we just went through, but let's say you've got a slightly different lathe, one with a gearbox. The program works fine with any a lathe without a gearbox, but if you have a gearbox, we have to include the gear ratios of all the gears. There's a special section on mini lathes here. Scroll down past all that. Mini lathes without gearboxes. Then we come to lathes with gearboxes. And under the Boxford list, we have the Norton Imperial gearbox, which includes my Boxford A. So I'll choose that. And it's got the gear ratios in there for that particular lathe. But there's also Myford ones in here. Chester, Chinese, couple of Chinese models. Colchester, Craftsman, Denham, Grizzly, Harrison, Hendy, High Mount, Nile, Qualos, Raglan, Smith Imperial, Toss, Ward, Yunnan, Shinwai, South Bend, and so it goes on. Actually, there's a special GTR calculator here for calculating the gear train ratio. So I've already entered this as being the Boxford lathe with a gearbox. Go back to the data entry. So we've just specified the lathe. Gear train design. We want, say, one compound gear, which looks like this. If that doesn't work, you can go to 2 compound gears, but it has a lot more solutions, but is a bit more complicated to set up. And in this section, you decide whether you're having automatic compound gears or not automatic. And for 90% of cases, you want automatic. The one we just did a minute ago with a particular compound gear of 36/34, we used not automatic, but generally in most cases we can use automatic. And that uses the standard change gears to make up pairs, so you don't have to enter a pair of gears. So that's our gear train design. Enter your own gears. And this is a list of gears or similar to the one we just had. It had 16 on the list we did a minute ago. We don't have a list of compound gears because we chose automatic, so the machine automatically chooses pairs of these gears to make up a compound pair. And next we want to specify what type of thread we want. Well, we already did that a minute ago. We changed this to a metric thread, so it's already set. And the acceptable error, I guess we'll stick with 1%, could go to 2 if you're desperate. And the pitch of the thread we want is 1.5 millimeters again, and we'll see what we get this time. So now we've got 190 solutions. Last time we only had 1, but we've got a lot of different gear combinations that are possible. So again, these are sorted in the lowest error first, and as we go up, the errors are higher and higher. So we generally want to choose something from near the top of the list, 0.0510. That's got a 16 stud gear, 46 compound combined with a 40 for compound 2, and connecting to a lead screw of 60. Again, we can draw this, and that's what it looks like. But this time the difference is that we've got a gearbox code of A4 at the bottom. And again, it looks as though they should fit together nicely. Fit test, no obvious problems. And the equations. With this set of change gears, we can actually produce compound gears that are useful. And in fact, we could produce that thread without having to buy any extra gears. Let's try a different metric thread, a little bit more difficult. It's 1.25. And we've already got all the other data in, so we don't have to enter it again. Just click Run. 153 solutions this time, still a lot, and still quite a few with very low error. So any of these all down here could be quite suitable. Say the first 16 options are quite suitable options. Here we're using a compound pair of 4648. This one is 1648. That would work, but it gets more difficult to fit other gears into this with such a big difference between the 2 compound gears. Let's look at that and see what I mean. So if the stud gear happened to be any smaller, there wouldn't be room to get it into this little gap here between these 2 compound gears. So it's better to have the 2 compound gears very close together in size. I'll try that first one, 5648. Now you can see these 2 gears are much closer together in size. So there's only a little difference in here, so we should be able to fit any gear. Say the lead screw gear had been a very small gear, it'll fit quite well into the small gap. any idler on these displays, it means that the compound gear can be replaced by an idler gear like this. Let's have a look at the draw diagram. And you see here we don't have a compound gear, we have a large idler gear, which can be of any size, typically 80 teeth on it, but that doesn't really matter. The stud gear is 16 and the lead screw gear is 40. And you can ignore the idler gear. If you wonder why, you need to have a look at my Understanding Gear Trains video. And before we ride the gear train, there's something else that's worth showing you. And let's use the same setup we've just put in to save us some time here. But instead of putting in a single thread of 1.25, we can actually select a range of threads or reference threads. Perhaps the easiest one to show you is reference threads. This gives you tables of all the different kinds of standard threads you might use. And first it does the metric threads, ISO standards, camera threads and everything. A whole range of different kinds of threads that you can choose. So let's say we want the standard ISO course. You click this button here, choose which diameter you want. Say it's a 6mm 1mm pitch or 8mm diameter with 1.25mm pitch. You can choose that and just return with that, and it now knows the pitch you want, so it can run the program with 1.25mm pitch. It also gives you a lot of other information about that thread. Now another alternative is to use 5B, which gives you a range of threads, and that's very useful if you're trying to test out a particular gear set to see what metric threads you can produce. So we can either put it in as range, say 4 to 8, that's for imperial, so we'd put say 0.25 in steps of 0.25, something like that, and you could do this range. Actually, in this case, I think it would be preferable to use a list of values instead. And this bit of text here shows you the lists of sizes. For the M series metric threads here, you would use this range of different thread sizes. That's a pretty long list of different threads it's going to have to calculate, and I think I'd be inclined to cut it down into a couple of smaller blocks. So let's try that one. And perhaps the smaller sizes aren't so necessary either, so I'll just choose those, copy that, and we go down to the place where you enter the threads as a list separated by commas, return to the menu. So we've just done 5B for entering a range of values, and we click run. This is an example where there's huge numbers of results, and it's giving us a warning that it will terminate after 500 different threads that's calculated. I can't imagine too many people wanting to look through a list of more than 500. It takes the program extra time as well, so it's displayed here how many milliseconds it's taken to do the calculations. The program, of course, doesn't run to completion and may miss out some useful results. The way to approach this is to go back to the menu, and I've got a button here so that you don't have to scroll through all 500. And although you might think that altering the list of results would help, it doesn't help much because of the way the program's designed. It goes through all the combinations of possible gears and then checks to see if it fits any of these threads on the list. So that actually makes it run quite efficiently, rather than running the whole program over and over again for each different thread size. But a better way of going back and correcting this problem is to reduce the amount of error you're willing to accept. So we saw a lot of results which were under about, say, 0.5%, even 0.25%. Try that. And press enter, and go back to our menu and click run and see what we do there. Now I've got 282 results, and the program wasn't terminated early, so we should have them all in here. And actually, let's scroll all the way to the bottom first. It said the program found solutions for every thread size. So if there was some thread size that got missed out because it just didn't work, it'll tell you here which thread sizes were not produced from the list. If you're really keen, you can go back to optional entries, and the first one is the number of results that are going to be displayed, and it's set to 500. You can set it to any number you like, but I don't think there's much benefit in producing more than 500 results. So we've actually got 500 threads here, and they are not sorted by error because of the fact we've got a whole lot of different sizes, and they have to be sorted by size. So it shows you that you can make 0.3mm pitch threads, 0.35, 0.4, 0.4, 0.45, lots of them, 0.5, etc. So the list goes down for a total of 500. So you can see you can make quite a range of different metric threads with that setup without buying yourself special compound gears. And that's it. One more thing I should mention, and that is if you are planning to get extra gears or compound gears, look seriously at having them made on a 3D printer. There are some people who've been making gears out of Delrin and turning those, and some of these are available on eBay, or if you can find a friend that's got a 3D printer, you can easily work out how to do it. One way is to go to McMaster Car, and they have gears for sale, but they also give you data files on how to produce them. I think they're mainly for CAD-CAM systems, but it might be worth looking at that. And Thingiverse is another place where you can find things to make on 3D printers. If you don't have a 3D printer yourself, it's certainly worth looking around in your local area, local libraries, and find if there is a local club that has printers available. I live in a fairly small town with a population of 30,000, and there's a place called the Invention Centre, and they've got 4 3D printers. They're buying an engineer's lathe with a milling attachment, and they have laser cutters and all laser etching systems, and all kinds of very interesting equipment which saves you from buying it yourself. So there are lots of options out there for producing gears that you may need. And people have had excellent results with using 3D printer gears. They seem to last forever, effectively. So certainly look into that option. This foray into metric-imperial conversions has kept me busy for a long time, and I found it very interesting, and I hope you found the video interesting. I was particularly pleased to be able to derive this equation for calculating the gear ratios for converting between metric and imperial lathes, and I hope people find it useful. And I think we've also demonstrated that the Ride the Gear Train can be very helpful before you go ahead and buy gears. If you do decide to buy a particular gear or combination pair, you can put them in the program and find out how many extra threads you will be able to produce with that before you even buy them. So I think it's very useful for all those different angles. It's surprising how many people find that they can produce the metric thread they want with the gears they already have, and saves them going out and buying gears. And if they do buy gears, often limits the number of gears they have to buy. I've had one customer say he was going to buy a dozen gears and ended up buying 3. So I hope you find this very helpful, and I'd love to have any feedback. So subscribe and give us a thumbs up and let us know what you think.